So what we'll talk about is part two, which covers 8 different units, 6 through 13. Unit 6 is composition and structure of the atmosphere. This is a picture of Earth and the Moon. The Moon's about one-sixth the size of the Earth. It's about 23,500 miles away. You could actually fit all the other planets in our solar system between the Earth and the Moon. If you put Venus, Mercury, and even Jupiter and Saturn and all the large planets, they would be able to fit in between the distance between the Earth and the Moon. So the Moon is important and affects tides and a lot of other atmospheric phenomenon here on Earth. So in our atmosphere, we have an atmosphere that's made up mostly of nitrogen and oxygen with other carbon dioxide, argon, and other elements. But the constant gases are the gases that are found most commonly in the lower 100 kilometers or the homosphere of the Earth. And when you get above that, the consistency and the makeup of the gases tends to vary more. So that's called the heterosphere above the homosphere. So about 100 kilometers, 60 miles up, the amount of gas is pretty homogeneous and similar, doesn't vary that much. And then as you get above that, it starts to vary more. So within the homosphere, nitrogen is about 78% of the air and oxygen is about 21%. And the variable gases are gases that significantly change depending on where you are in the atmosphere, how high or how low you are. And those are carbon dioxide, water vapor, ozone, and other elements. Aerosols are fine small little particles, usually less than a micron. If a particle is larger than a micron, it's considered dust. If it's smaller than a micron, it's considered aerosol. A micron, 1 million microns are in 1 meter, so that's how small that is. So there are some trace elements in the atmosphere that can affect the atmosphere that are considered aerosols or particles. So here's a little more information on the composition of the atmosphere. About 78% is nitrogen, 21% is oxygen, and argon is the third most common substance, just under 1%. Argon is a noble gas, which means it's a gas that does not interact with or mix with others. It doesn't react to others. It sort of is on its own. There's about 23 times more argon in the atmosphere than there is carbon dioxide, which we're probably familiar with as a potent greenhouse gas. Carbon dioxide is 0.073% of air in our atmosphere, roughly. So relatively small, but still a very influential uh, element in our atmosphere. The most common form of oxygen is a molecular oxygen, which are two oxygen atoms that are bound together into a molecule of oxygen made up of two oxygen atoms. Atomic oxygen is when you have a single oxygen atom on its own, not merged with another oxygen atom. Those are actually very rare. And then ozone is when you have three oxygen atoms that are merged into one molecule made up of three atoms of oxygen. Those are up usually in the stratosphere, usually about 30,000 miles up in what's sometimes called the ozone layer, where most of the ozone is. So these are the three main kinds of oxygen. The most common is molecular oxygen. That's, of course, what we breathe in. We breathe out carbon dioxide, and plants and algae breathe in carbon dioxide and breathe out oxygen, which is why it's important to have plants and algae and living matter in order to generate oxygen. So oxygen has varied significantly over the Earth's past. Going back 3 billion years, there's very little. And about 2 billion years into the past, it was about 3%. Then it started to increase significantly for about 1 billion years as more plants and algae started to become more common on Earth. They generated more oxygen. About 300 million years ago, at the very beginning of the dinosaurs, the oxygen level was much higher than it is now, probably about 32%, it's estimated. Now it's roughly about 20% of the elements in the air is oxygen. So it has very significantly, peaking about 300 million years ago and being about 20% now and going back about 100 million years. So ozone is, again, is when you have three molecules of oxygen merged together, three atoms of oxygen merged together. And this is an important layer because ozone filters out ultraviolet rays from the sun. And if ultraviolet rays are too high, they can increase the risk of skin cancer, they can impair human immune systems, and they can cause a lot of other issues and problems. In the early 80s, it was determined that chlorofluorocarbons, an element found in cans of hairspray and other household items and air conditioners, were getting into the atmosphere and breaking down the ozone layer. These chemicals were interacting with ozone and breaking them apart. and that was creating what was called an ozone hole, especially over Antarctica, that formed during the Antarctic winter because it was very cold there, and that's where the ozone hole was most likely to form. The chlorofluorocarbons were phased out of aerosols in the 80s and early 90s. I remember hearing about that growing up. And now the amount of chlorofluorocarbons has significantly decreased, but some of the damage is still done. This is a picture of the ozone layer in 1979 and as 2008. And as you can see, the chemicals have done significant damage. The good news is scientists think these chlorofluorocarbons tend to hang around for about 50 to 100 years. And it's estimated that around the year 2070, that ozone layers will be probably back to roughly normal levels over Antarctica. We still are emitting some of these chlorofluorocarbons from refrigerators and air conditioning units that are in landfills that still tend to seep out these chemicals. But by phasing them out, it has vastly cut down on the amount of these chlorofluorocarbons in the atmosphere. And scientists think by 2070, it should be roughly close to back to normal. And what we have in our atmosphere should have worked themselves out by then. So hopefully by 2070, it'll be back to normal. And thankfully, very few people live anywhere near Antarctica, except for a couple scientists, so it hasn't affected too many humans directly. So this shows the variation in carbon dioxide on Earth over the millions of years. We've seen how oxygen can vary. Carbon dioxide also varied significantly. About 500 to 400 million years ago, carbon dioxide levels were significantly higher than they are now, roughly 22% of the atmosphere going back about 550 years. Then it decreased significantly. About 300 million years ago was about where it is now. Then it peaked, then declined a bit, and now they're less than 1%. So there has been changes in the composition of the Earth's atmosphere over hundreds of millions and billions of years. So you might wonder, how would we know what carbon dioxide levels were 100, 200, 300 million years ago? Well, scientists can determine some of this by doing tests on ice core samples. Basically, ice core samples are long tubes of ice that are drilled into Antarctica or anywhere where they've had ice for a long time. And they can, with a high degree of accuracy, go back and look at layers of ice just like rings on a tree with a high degree of accuracy, almost down to the exact year. Drill a layer of ice, do a test on little air bubbles contained in that layer of ice, and determine what the atmosphere was like when that air bubble was formed hundreds or maybe thousands of years ago. Before that, it's a little more of an estimate, but going back several hundred years, there's a pretty good information on what the carbon dioxide levels were like. So CO2, before 1960, there are some ice core samples that we have. Since 1960, there are observatories in Hawaii and elsewhere that can just read the atmosphere and more easily and more precisely. So this chart shows information that was gathered studying carbon dioxide going back over the years. And since 1960, most of it has been from the Mauna Loa air samples at the top of a mountain on Maui in Hawaii. This is the observation top at the top of the mountain in Hawaii. My wife and I actually, when we went on our honeymoon, went to the top of a mountain in Maui and actually biked down the mountain. It was a lot of fun. You could go up there in big buses. You'd have hundreds of other people. You get there about 4 o'clock in the morning, watch the sunrise. It was very cold up there. And then you'd bike down the mountain, which was easy because it was, of course, a gentle slope the whole way down. So it was a lot of fun. And on the bottom, you can see these are examples of ice cores, and you can see these are long cylindrical shaped pieces of ice that are drilled into ice in Antarctica, Greenland. And then you can see the little bubbles trapped in them that scientists can then study to see what the air makeup was going back several hundreds or thousands of years. So as you go up in the atmosphere, the temperature tends to cool, but it does not cool consistently. This is something that even I just kind of learned when I started teaching this. It gets colder as you go up, as you would expect, till you get to the top of the troposphere at about 15,000 kilometers. And then there's an area called the tropopause, where the troposphere merges into the stratosphere. And at that time, the air actually starts to get warmer as you go up until you get to the top of the stratosphere at about 50,000 kilometers. And then there's something called the stratopause. And then it starts to get colder again as you go into the mesosphere. The meso means middle. So Mesoamerica is the central part of America. And then as you go up towards the mesosphere, it gets colder until you get to the very top of that. And then there's the mesopause. And then the highest layer in the atmosphere is called the thermosphere. And once you get into that, the atmosphere actually starts to get warmer again. So it doesn't consistently get colder. It gets colder than warmer and then colder than warmer, depending on how high up you are in which of these four sections of the atmosphere you're in. So one interesting atmospheric phenomenon is the northern lights or the aurora borealis. This picture was taken above the North Atlantic Ocean in 2014, and those are caused by collisions of ionized particles with gas molecules in the Earth's atmosphere at the higher latitudes. I actually saw the northern lights when I was camping a long time ago in the mid 90s in northern Michigan. It was actually the summer. You usually see them more in the winter. But I remember I was woken up by my parents at about 1 a.m. They said, "Hey, you got to see this." So even though it was summer, it was cold out. It was probably in the upper 40s. And then we walked to a dark part of the park and we were able to see these shimmering movements of light in the atmosphere and these green waves that kind of went through the night. It was really very pretty. And then when we were in South Haven last summer, we heard that we might be able to see the northern lights from South Haven in late August, but we were not able to. We looked around, there were some other people on the beach, but we couldn't see it. So you see it, the further north you are, generally the colder it is, the more likely you are to see it, but it's kind of inconsistent when it appears. So Unit 7, temperatures of the lower atmosphere. This is a screenshot of what typical temperatures would be in January in the northern hemisphere. And as you can see, the Arctic is significantly cooler, and then as you go down, it gets warmer. But where you have continents like North America, it gets colder than where you have maritime environments like the North Atlantic. So as you're further into a continent, it's further away from the warming effects of the ocean. It gets colder. So large land masses like North America and Asia often have very cold cities during the winter deep inside their interiors. And then those same places often have very hot summers because of a continental atmosphere where you have big swings in temperature. So temperature and temperature scales. What is temperature? Temperature is an index that measures the thermal energy of matter. So basically, how much energy is contained in matter, whether it's air or water or a metal object. And there are different ways of measuring it. Far and away, the most common is Celsius. This is when you have water freeze at 0, boil at 100, and then between that you have 100 equal intervals of change in temperature. Then it goes above and below that. Other kinds of ways to measure is Fahrenheit and Kelvin. Kelvin is basically the same as Celsius as far as the degrees, but Kelvin starts at absolute 0, which is negative 373 degrees negative 373 degrees in Fahrenheit. So basically, that's the level where almost all molecular movement freezes, where it's theoretically impossible to get any colder. Then from there, using the Kelvin scale, it goes up at the same degrees that Celsius does. So the creator of the Celsius scale, which almost everyone uses except the US and a few other countries, is a guy named Celsius. He was a Swedish astronomer, and he came up with the idea. His idea wasn't really implemented until after his death, but he came up with the idea of having a system of measurement where boiling water would actually be 0, freezing water would be 100, and then as something got colder, its number would increase. The logic was, since you can't get hotter than boiling water, why do we make that the start? We'll make that 0, and then we'll go backwards. And the larger the number, the colder something is. Scientists took his idea of having freezing and boiling water as a benchmark, but then they flipped it to what we know today: 0 freezing, 100 Celsius is boiling, and so on. So most scientists didn't understand why you'd have an inverted scale like that, and they took some of his concepts, but then switched them to what we know today. So in the 1860s, there were a lot of scientists doing important research on the atmosphere, and two of the more famous scientists is James Glaisher and his assistant Coxwell. During the 1860s, they had a series of hot air balloon flights where they went way up into the atmosphere, higher than anyone had ever gone, and took measurements on the temperature, air pressure, and numerous other things, and got a lot of very useful information about the atmosphere that we now know today. They very loosely based a movie on it called The Aeronauts, which I have not seen yet. Apparently, Eddie Redmayne plays Glacier, and Felicia Jones plays Coxwell, or his assistant. I don't know how closely they based it on him, but I guess they thought they wanted to have a female lead in this but it's very loosely inspired by these two real scientists who did scientific research in the 1860s. So stability in the atmosphere, when the atmosphere and air is over water, it often moves on to land, where especially if it's summertime, there's often a significant increase in temperature. Lake Michigan is a lot cooler, say in July or August, than land over Lake Michigan would be, or land over Michigan would be. So you often have moist air moving over land, coming in contact with suddenly hotter temperatures, and that can create instability, having that sudden change in temperature. And that's when you often have clouds. So in this picture on the bottom left, there's Lake Michigan in blue, and then you can see clouds form over the peninsula of Michigan, and same with Florida. This is Florida on the right. The Gulf of Mexico is on the left, and as moist air from the Gulf of Mexico moves over Florida, that forms clouds. So that's a fairly common pattern of moist air moving away from bodies of water over land and then becoming cloudy and unstable and having rain and thunderstorms when that happens. So usually, as we studied, as you get higher, things get cooler, at least for a little while till you get to the end of the lowest layer of air. But occasionally you'll have air get cooler, then get warmer, and then get cooler again. And when you have a thin layer of warm air over a colder layer of air, that's called an inversion layer. And sometimes these inversion layers can be a major problem in big cities because they have a tendency of trapping smog underneath them. So an inversion layer over Mexico City or London or Los Angeles can act like a blanket that will hold smoggy, dirty air over the city and prevent it from being blown away or getting dissipated in the upper atmosphere. So inversion layers can be a problem, especially in areas prone to them like Los Angeles, where it can trap smoggy, dirty air underneath a layer of warmer air above it. London in 1952 had a horrible inversion layer that settled in over the city in December. And as you can see in this picture, London used a lot of coal-fired power plants at the time. It was a very smoggy, sooty city, and it had a horrible blanket of pollution that could not dissipate for several days. It was about a week and a half of almost pitch black air from all the smog. And actually, there are about 10 to 12,000 deaths from respiratory problems that happened because of this smog. People were rushed to the hospital. The hospitals were overwhelmed, and thousands of people died because of this terrible smog that settled in over London. So smog can be deadly if you have real high concentrations of it. That was a little unusual. Coal is used less often than it used to be. Nuclear power, natural gas, wind, solar, and other things are more common. So it's not as much of a problem as it used to be, but it was a big problem in London in the 1950s. This is an example of Los Angeles. In addition to trapping smog, dust domes can also form over large cities where localized weather tends to trap dusty, dirty air over a large urban area, and that also can have a hard time dissipating. LA actually has, they were one of the most important states in phasing out lead from our gasoline. California was kind of a leader in that. Detroit and the automakers didn't want to do that, but in the 1970s, lead was phased out, and the air quality in LA and most of the US is actually a lot better now than it was during the 1960s and 70s before tighter rules were put in place to regulate air pollution. So it's actually better now than it would have been 40 or 50 years ago. So horizontal distribution of temperatures. There are natural cycles that the temperature on Earth goes through. They're temporal cycles. These are cycles that are kind of based on daily activity. There's the daily cycle of heat. It gets warmer during the day and cooler at night typically. And then there's the annual cycle of temperatures getting warmer in the spring and summer and cooling them off in the fall and winter. And then there are also changes based on not just the daily and yearly cycles, but also water versus continental. A maritime effect is areas over the ocean have fewer temperature extremes. They're cooler in the summer, usually warmer in the winter. Again, that's called the maritime effect. And as you get further inland, the air is drier. There's less of a maritime effect, and you have greater temperature swings in temperatures. So the maritime versus continental climates are also a major influencer in weather. And global temperature variations, again, can vary by seasonal variations. And you can see on isotherms where you'll have changes in temperatures. We talked a little bit about isotherms before. That's where you have a map or you have a line that shows where a separation of a topography could be or temperature could be. And isotherms kind of show where there's a change in temperature from one layer to another, from 60 degrees to 70s and so on. So this is an example of a map that uses an isotherm to show a temperature range in Celsius. And on the top, this is the annual surface temperature of the ocean. The top is what the oceans of the world are in early in the year, in the spring, and then in the bottom, you have the temperatures later on. So as you can see in the bottom, in July and August, the northern oceans, the Pacific, the North Pacific, is the warmest in August and September. You might think it wouldn't be, but it is the warmest in August and September because the ocean takes a while to heat up, so it doesn't peak in June or early July. And then, as you can see, it's much cooler in the southern hemisphere during that same time period. And the southern hemisphere is actually warmest in January and December, or a little bit after January and December. So the water takes longer to heat and cool, and because of that, the North Pacific is actually warmest in September. So this is comparing two U.S. cities that have a continental climate, Omaha, Nebraska, deep inside the interior of the country, and more of a maritime climate, San Francisco. San Francisco's climate would probably be classified as a Mediterranean climate, but it's a cool Mediterranean climate, kind of a transition between a Mediterranean climate and a marine West Coast climate. And as you can see, Omaha during the summer, its warmest month is July, and it averages about 78 degrees for a high in July. And then San Francisco, even though it's further south, is significantly cooler, averaging probably about 64 degrees high during that same time period. And during the winter, of course, San Francisco is significantly warmer. So being on the ocean, San Francisco has a consistent cool ocean breeze that keeps it a fairly constant temperature, usually above 60 and below, above 50 and below 65 almost all year round. Like Omaha, like Michigan, has wild swings because of its continental climate. So Omaha, Nebraska is on the top there, and San Francisco is on the bottom. I've been to San Francisco. It's a beautiful city. When I was there, it was fairly warm. I heard that was unusual. We were there, it was the low to mid 70s and sunny for about 3 or 4 days in a row. And I was told, oh, that's unheard of. You guys got lucky. But it was very nice when I was there. And one of the most extreme examples of a continental climate is Varvayosk. Varvayosk is a city in the north central part above the Arctic Circle in Russia. And as you can see, based on this chart here, it gets quite warm in the summer, well, relatively warm, getting it to about 64 degrees for an average high in July, and then plummeting to an incredibly low, roughly 40 degrees Fahrenheit and Celsius. They converge at 40 degrees during the winter. So huge swings in temperature, warm in the summer, incredibly cold during the winter because of its continental climate far away from the oceans. We talked a little bit about the urban heat island effect. We talked about how when you have a large city with lots of concrete and cars and air conditioners, the air-conditioned buildings kind of vent out the heat into the area around it, and that can lead to significantly warmer temperatures in an urban area than nearby suburban or rural areas. So where it's woodsy, where there's farmlands and trees, that's significantly cooler than a couple miles away in an urban area without much shade and with lots of cars and concrete and asphalt and parking lots. So this is kind of an example of the urban heat island idea. In addition to urban heat island effect, temperatures can change based on the wind chill. The windier it is, the colder an area feels. This is kind of a chart that shows the danger of frostbite when you have a moderate wind compared to a strong wind. And again, wind on your face will feel cooler than if it isn't windy at the same temperature. And then kind of on the opposite extreme is the humidity or heat index. And this is a chart that shows that when it's more humid and there's more moisture in the air, it's not as easy to get rid of your body heat. You can't sweat as easily because the air itself is more humid, so the sweat doesn't dissipate as quickly. And 90 degrees and humid, 90% humidity will feel a lot hotter than if it's 90 degrees in a dry environment like a desert, where you can sweat more easily and you feel a little cooler. So when people often say it's a dry heat, they're referring to a low humidity means that even if it's the same temperature, it will feel cooler than the same temperature where it's more humid. So air pressure and winds. This is a picture of atmospheric pressure. Atmospheric pressure, wind moves from high pressure areas towards low pressure areas. You can imagine if you're in a bathroom and it's steamy, and then you open up the bathroom door real quick, the steam escapes from the bathroom into the hallway, which is less dense and cooler compared to there. And in the same way, high pressure area, air moves from high pressure areas to low pressure areas. Um, at sea level, air pressure dissipates and gets thinner as you go higher up in elevation. But at sea level, there's about 14.7 pounds per square inch of pressure at sea level. So that's kind of the standard that's used around the world for standard sea level air pressure. So air pressure is measured using a barometer, and a barometer was invented by Torricelli, an Italian inventor, in 1643. He essentially created a device where he had mercury inside. As you can kind of see here, this diagram here, there's a liquid inside of a vacuum, and then the greater the air pressure, the more it pushed up on the liquid inside. And he was able to use this to create a consistent way of measuring air pressure. And again, at sea level, it's highest. And then as you get higher in elevation, it gets thinner and thinner. So this chart here shows that sea level um, at air pressure at sea level is significantly stronger than it is higher up. And if you're at the top of Mount Everest, which is a little over 29,000 feet, the air pressure will be significantly thinner than it is less than 40% the air pressure of sea level. So that's why when people climb Mount Everest or tall mountains, they'll often bring oxygen with them so they can breathe in oxygen. And otherwise, you can get lightheaded and dizzy, and it can affect your ability to walk. So here is a bunch of people bringing oxygen tanks up Mount Everest while they're climbing it. I've heard there's a problem with thieves trying to steal oxygen tanks from other people so they don't have to lug their own heavy oxygen tanks up, and it's kind of a minor issue on Mount Everest. So this is kind of a snapshot of what pressure gradient forces would look like. If you have an area where you have low pressure on the surface and higher pressure higher up, you'll often have warm air coming up and then being lifted up into the atmosphere. And then the opposite happens if the higher pressure is cooler and denser, and then the surface is less dense. You'll have that high pressure center come down, and then these wind socks kind of demonstrate where the air is moving. So essentially, this kind of demonstrates that air pressure moves vertically from high pressure to lower pressure as well as horizontally. So an important concept to know and understand is the Coriolis effect. This is essentially the Earth spins around, and then as it spins, it alters the atmosphere of the Earth. And an example they give here is on the left, there's two people on a merry-go-round, and then someone throws a ball, and the person who threw the ball to his partner, the ball goes straight towards the third person, but it looks as if it's bending, and that's again because of the rotation of the merry-go-round, or the rotation of the Earth. So the Coriolis effect can change wind patterns depending on the latitude, making wind move from the west to the east or east to the west, depending on where it is in the latitude. So the Coriolis effect has a significant effect on the environment. Another issue affecting wind is friction. Friction is something that acts opposite of the wind. So a good example of that would just be woods or forests, or anything that kind of breaks the wind naturally would slow down the wind and increase the friction, and therefore reduce the wind speed. So if you're on the top of Mount Everest, there'd be very little friction. If you're in an area where you have lots of trees and bushes, there would be more friction, and it would slow the wind down. This is kind of an example of two extremes. On the left would be an example of a natural low friction environment. That's the Bonneville Flats, Salt Flats in Utah. So this is an area where it's an ancient abandoned lake bed. There used to be water there, but it evaporated. Now it's a wide salt flat. They test race cars there from time to time. And then the opposite extreme, a high friction environment, would be Hartwick Pines State Park in Michigan. There you have lots of trees and bushes. So if there was a 20-mile-an-hour wind, you'd feel it a lot more in the salt flats than you would if you were in the forests of Michigan or elsewhere. So surface pressure systems, a low pressure system, a general term for a large low pressure system is a cyclone. You've probably heard of the phrase cyclone. Tornadoes and hurricanes are all kinds of cyclones. It's basically a large low pressure center where you have wind moving around the low pressure center, moving from the high pressure areas towards the low pressure center in a circular motion. In the northern hemisphere, cyclones will spin counterclockwise. In the southern hemisphere, it's the opposite, it's clockwise. But this is an example of winds in the northern hemisphere spinning around a low pressure center. And then an anticyclone in the northern hemisphere will be the opposite, where you have a high pressure center and wind moving away from that. Anticyclones are not as dramatic. It's hard to even see if you're in one. Usually, an anticyclone just means nice weather, relatively stable weather, not a lot of strong winds, and not a lot of clouds. And then cyclones are where you get the storms like tornadoes and hurricanes and so on. Another local wind system, some wind systems that appear at a local level are sea breeze, mountain breeze, and a few others. The sea breeze is during the day, you'll often have wind that will move from the ocean onto land, moving from a higher pressure area to lower pressure area, moving usually from cooler to a warmer environment. And then as it cools, the earth heats up. When it gets colder, the system reverses itself, and then you tend to have wind moving from the land towards the sea at night. So if you ever hear of a breeze, sea breeze, wind breeze, the name is where the wind is coming from. So a sea breeze is coming from the sea. A land breeze will be wind coming from the land towards the sea. Another similar phenomenon is mountain breeze versus valley breeze. During the day, it's common in mountainous or hilly areas to have wind come from the valley up into the mountains as hotter, denser air is moving up into the mountainous areas that are a little cooler. Then, as that heats up and the northern parts and the higher up areas get a little warmer, night comes, then that pattern reverses itself, and you have cooler air from the mountains coming down into the valley at night. So these are examples of mountain breezes versus valley breezes. Valley breezes when it goes from the valley into the mountains, and the mountains is reversed of that. So circulation patterns of the atmosphere. Unit 9 talks about how the air moves around the globe at a global level. This is here you have clouds forming over Easter Island in the southern Pacific. So this is an example of a simplified version of the Earth. If there was no rotation, it removes the Coriolis effect and kind of imagines what the Earth would be like if it wasn't tilted at 23 degrees and if it didn't spin. You'd have a low pressure center around the equator. You'd have air moving along the surface of the Earth towards the equator, then moving up and then towards the poles higher up, forming this sort of this cell you see here, uh, moving from the equator to the poles and so on. And then the equator would be a low pressure center. And then the next slide kind of complicates the situation. This takes into effect what the rotation of the Earth would do. And when you add the rotation of the Earth, things get a little more complicated. The ITCZ is the intertropical convergent zone, and that's an area of relatively low wind along the equator. And in the northern hemisphere, up to about 30 degrees, winds consistently move from the east towards the west. When you get north of 30 degrees, north and the same south in the southern hemisphere, the wind tends to go from west to east, and those are called westerlies. So in Michigan, we're at 32 degrees latitude. Almost all the wind blows from the west towards the east. So westerly winds coming from the west is the norm. And then once you get above 60 degrees latitude, this trend tends to reverse itself again, and then wind tends to go from the east towards the west. So these are kind of global wind patterns when you take into effect the rotation of the Earth. So things get a little more complicated once you have that. These major cells, these circular wind patterns, are the Hadley cell from the equator to the 30-degree latitude, the Ferrel cell, and then the polar cell on the top and bottom parts of the globe. So those are the three major cells of wind moving around the Earth. So this is kind of the same idea, but you're looking at it from a cross section. So this is kind of interesting. This is the equator. Again, wind tends to move up from the equator up into the atmosphere, forming the circular pattern, the Hadley cell, the Ferrel cell, and the polar cell. And then between these cells, at the top of the Hadley and the Ferrel cell, you have the subpolar jet stream. This is a consistent, strong stream of wind that blows along roughly 30 degrees north and south latitude. And then a similar polar jet stream forms about 60 degrees north and south, where you have a similar thing where you have the Ferrel cell meeting the polar cell, and where they meet, there's a strong, consistent polar jet of strong wind that circles around the Earth. And this is the global mean sea level pressure in millibars, and January in A and July in B. So there is some change in air pressure depending on what time of year it is. And as you can see in January, there's a lower pressure in the northern hemisphere and a little higher pressure in the southern hemisphere. And then that trend tends to reverse during the opposite months. So you can see there's a large low pressure center right over Central Asia during January. So that means you could have cold weather and some storms moving in. And then there's a very high pressure center kind of over the North Atlantic. And then in July during the summer, you have a low pressure center in the Himalayas. That's what kind of creates the monsoon. Moist air from the Indian Ocean moves into the low pressure center near the Himalayas, bringing in rain and so on. So there's, as you can see, kind of changes in sea level pressure. You'll also notice too that there's consistently, when you get 60 degrees south latitude, there is very little land until you get to Antarctica. And because of that, you have very consistent temperature and wind patterns. So that's why scientists consider the Southern Ocean, the area south of 60 degrees latitude in the Southern Hemisphere, to kind of be its own ocean. Its properties are distinct than the other parts of the Pacific and the Indian Ocean and the Atlantic because there's strong, consistent wind. There's very little land mass in that part of the Earth to break up the wind, and it kind of has its own unique patterns of weather and temperature. Here's a side view of the Hadley cell in circulation. Again, this is the cell that's north of the tropical areas from 30 degrees latitude to about 60 degrees latitude. And here is the intertropical convergent zone. This is an area along the equator that moves slightly during whatever time of year it is, and it's usually an area that has consistent rain, but not incredibly strong winds. And as you can see, during the winter, it peaks a little bit below the equator, and then during the summer, it kind of moves above, significantly above the equator, up to the northern parts of India. So the monsoon is Arabic for seasonal, and monsoon winds are winds that are seasonal really anywhere around the world, but what's really known is the South Asian monsoon winds, and these are winds that move from the Indian Ocean, where it's high pressure, up to the Himalayas, which is lower pressure by comparison, and bring lots of rain and moisture into India during their wet season, during their summer. Excuse me. And then during the winter, this pattern reverses. It gets drier. You have colder temperatures and drier temperatures. And then you have a significant amount of time, several months, where it's drier. Some trees in India actually drop their leaves during their winter, the same way our leaves would do it. They do it due to a lack of rain and moisture as opposed to temperature. But essentially, this monsoon is caused by movements of low pressure area to high pressure area and so on. So this is an aerial photo of kind of northern India where it butts up against the Himalayan mountains. You can see here on the right, these are the highly productive farmlands of northern India. They have good soil, they have lots of water and rain, and it butts up against the Himalayas. And this is what it would look like if you were to live in this area here. This is kind of northern India, right up against the Himalayan mountains. So very beautiful area to live, and some of the most productive farmland in the world, with some of the highest population density in the world, along with eastern China. So this here is a slide of ocean surface winds, and you can kind of see certain areas have more consistent wind than others. This picture was taken with a QuickSat satellite that was created in 1999, and it was designed to look specifically at Pacific weather patterns, especially El Nino and La Nina patterns. And it was in operation for about 18 years before it was retired. But it's known for being built in about less than a year, and it was on time and on budget, and it gathered a lot of very useful information on weather patterns in the Pacific for about 18 years before it was retired. We'll talk a little about circulation of the world's oceans. Again, all the world's oceans are, of course, interconnected, and we generally break them down into 5 oceans. But there are surface currents that are influenced by the wind, there are deep ocean currents, and then there are air-to-sea interactions like El Nino and other large-scale weather patterns. So the ocean, of course, varies significantly in depth. It's broken down roughly into three layers. The top layer is called the mixed layer, and this mixed layer goes down to about 100, about 75 meters. And this is a thin layer that's influenced by the air and influenced by the wind and the sun and so on. And it has a lot of plant and animal life in it. Then, as you get below the mixed layer, about 75 meters down to about 1 kilometer down, you have called the thermocline. And this is when there's a sharp drop in temperature. There's not much variation in temperature in the highest mixed layer, and there's not much variation in temperature below the thermocline. But as you can see here, the thermocline layer from 75 meters down to 1 kilometer or 100 meters is where you have the biggest drop in temperature. Below that, there's very little sunlight and there's very little temperature change when you're below the thermocline. So that's called the deep ocean layer. The deep ocean layer below 1 kilometer is 97% of all the volume of water in the ocean, and it's consistently dark and cold. This here is a photograph taken from space of the Gulf Stream. And the Gulf Stream is a major sort of river of warm water that moves from the Caribbean and from the Gulf up along the east coast of the US and then out into the North Atlantic. And because of the Gulf Stream, Great Britain, France, and other parts of Western Europe are consistently warmer than they are at similar latitudes in Canada and North America, because this warm stream of warm air has a moderating effect on the environment in Europe. So Great Britain, Scotland, Ireland, France, and England, and so on are significantly warmer than similar cities at the same latitude in Canada and elsewhere in the world. So this stream of water moves at about 5 miles an hour. It's kind of like a river of water in the ocean moving out into the Atlantic. Here's another picture of the Gulf Stream. It kind of shows the speed that it moves, and as you can see, it kind of dissipates once it gets into the North Atlantic. These little loops are called gyres. Those are kind of loops of continuously moving water in the ocean. And this is a surface current and gyres in the ocean. This is sort of a general picture of the ocean. It's a generic ocean where you have continents on both sides and the equator here, and it kind of shows the general pattern of movement. Warm water moves up north where it mixes with colder water in the north and south parts of the ocean where they're closer to the north and southern poles. And it kind of forms these continuous loops of movement of warm and cold air. So there's a general picture of movement of warm and cold water in the ocean. Where you have lots of cold water from the bottom parts of the ocean coming up to the surface and mixing and merging with it, that's called upwelling. And upwelling is actually some of the most productive parts of the ocean. These are oceans that have the highest amounts of chlorophyll and plankton and so on. So they also tend to attract the most fish. So in this map, areas where you have tan and yellow are areas where there's a lot of productivity in plankton and plant matter in the water. And areas that are deep blue are sort of almost ocean deserts with very little life, far fewer fish, a lot less plankton. So along the equator and north of about 40 yards latitude, there's a lot more plankton and plant matter in the ocean, and therefore a lot more fish. And just north and south of the equator, but below 40 degrees latitude, longitude, it's usually a lot less productive with far fewer fish and plants and so on. And this is a more detailed, realistic picture of ocean currents. As you can see here, there are some strong warm and cold currents all along the Pacific and the Atlantic. There's a very strong cold current moving from Alaska down the western part of the US. So the water in Los Angeles would be a lot colder than it would be in Miami or northern Florida, even though they're at similar latitudes, because they have this current of cold air coming from Alaska coming down. And the Galapagos Islands, which are near the equator, actually have fairly cold water surrounding them as well. And then, as you can see here in red, you have warm ocean currents going along the eastern part of the US towards Europe in what's called the North Atlantic Drift as it gets away from North America. And then in the southern hemisphere, a similar pattern of strong currents moving from the Antarctic towards the equator, that's cold, and warm water moving from the equator towards the south, that's warm, forming circular patterns. So this is an example of some of the large-scale patterns deep in the ocean's water. These are ocean patterns that are not necessarily influenced by wind because it's too deep down. These are called global conveyor belts of water. And this is similar to the previous map, but this is temperature patterns deep down in the ocean where the wind is less of an influence. And here you have this continuing pattern of cold water coming from Greenland down the Atlantic, then pushing across the top of Antarctica, then getting up, moving up into the Indian Ocean where it becomes warmer, then coming down again over the Atlantic and so on. So these are kind of conveyor belts of warm and cold water that circulate around the globe in our oceans. So you've probably heard a little about El Nino and La Nina. Those are weather patterns that affect the Pacific, specifically the Philippines and South America, and areas along the Pacific. Essentially, on the top picture, you have a normal Pacific weather patterns, and usually you have trade winds blowing from the west, from the east towards South America, towards the west, towards the Philippines, and so on. And occasionally, during El Nino, about every 3 to 4 years, this pattern kind of reverses, and then you have trade winds blowing from the west towards the east, and then you often have rain in South America, and then drier conditions on the western part of the Pacific. And then you've probably heard of La Nina. A La Nina is sort of a typical weather patterns, but driven to the extreme, where you have even stronger winds blowing towards the west, and even heavier rain on the western part of the Pacific, and even drier conditions along South America. So El Nino is what you might have heard most of. They happen roughly every 3 to 4 years. How or why, it's not entirely known. But this one, weather patterns in the Pacific kind of reverse, and places get weather they're not typically used to having. It usually means heavy rain in South America. So in North America, El Nino and La Nina patterns. El Nino in North America usually means wet, cool weather in California and Mexico and so on. And then La Nina patterns usually mean drier weather and a high pressure system where you usually have clear skies and drier weather, but sometimes that can lead to droughts and other problems. So that's how El Nino and La Nina would affect North America. So Unit 11, atmospheric moisture and water balance. We'll talk a little about properties of water in the slide here. The picture here, you see mist kind of forming at the bottom of a valley in a mountain in Hawaii. And of course, water has three main phases. It's one of the few things that has three phases within a temperature range that people come into contact with on a regular basis. Of course, when it's liquid, its molecules are kind of jumbled and irregular. And then if that heats up, addition of heat causes vaporization, which leads water to become a gas, where the molecules are far less packed tight and more dissipated and separated. That would be steam and water vapor. And then if you start out with water and you significantly cool it, if you freeze it, the heat is released and then that forms solid ice. And then water, when it's in its ice form, the molecules form a very rigid pattern. They're not irregular like they would be if they were liquid or gas. And then occasionally you can have something move from ice directly to water vapor, which is called sublimation. And that's when you add heat to ice and it can move from ice directly to water vapor. Then if it moves directly from water vapor to ice, it's called deposition. So this kind of shows the different phases of water and what has to happen to move it from one phase to another. So the hydrologic cycle is kind of the pattern that water often moves through in the natural environment. It will come in and come to land as rain, then it will become runoff or be absorbed into the water. Then it can land on top of the ocean or land on land, and then it can go up in the form of evaporation, forming clouds. And then water can just kind of endlessly circulate between rain, runoff, and evaporation in this pattern where it moves from place to place in this endless cycle caused by heat. And the vast majority of water on Earth, of course, is in the ocean. 97.2% of all the water is ocean water, and that's salty. A small portion of the Earth's water is fresh water, just under 3%. And if you look at that roughly 3% and expand that, you can see that a large amount of that 3% is ice sheets and glaciers. About 2.15% of all the world's water is ice sheets and glaciers. Groundwater below 700 meters is 0.3%, and groundwater above that is 0.7%. And then a tiny amount of that is fresh water in the form of lakes and so on. And if you look at that tiny sliver, about 0.017% of the Earth's water is fresh water and saline lakes and seas. Saline water is water that's not as salty as the ocean, but not fresh water either, sometimes called brackish water. The Caspian Sea has water that's about one-third as salty as the ocean. So it's not a freshwater lake, but it's not as salty as the ocean either. So that's called saline water. So only a small fraction of the Earth's water is fresh water that is in the form of lakes or rivers that we have easy access to. The rest of it is either ocean water or often frozen in ice or underground in aquifers or something like that. So among the world's largest freshwater lakes, we like to think Lake Superior is the biggest, and it is area-wise, if you don't count the Caspian Sea. But the largest lake in the world by volume of water is Lake Baikal, and this is in south central part of Russia in the southern part of Siberia. This is an incredibly old and incredibly deep lake. Scientists believe the lake is over 1 million years old. Most of the Great Lakes are 12 to 14,000 years old, relatively new. And because Lake Baikal is so deep, it actually contains more water than all of the Great Lakes put together. And this picture here is kind of a cross section of the lakes. Lake Baikal is over a mile deep. It's the only freshwater lake that has seals. They have their own seals, their own unique flora and fauna. And then if you were to compare Lake Baikal to Lake Superior and Lake Huron, this is what they would look like by size and depth and so on. And Lake Superior and, of course, Lake Huron are kind of the same lake. They're connected with the Straits of Mackinac, but they're considered separate lakes. Lake Erie is far and away the shallowest, and then Lake Ontario is a lot lower than the other Great Lakes. And then Lake Ontario eventually goes to the St. Lawrence River and empties out into the Atlantic Ocean. So these are some of the largest freshwater lakes in the world. Lake Baikal is the largest by volume of water. So water usage is a major concern. You've probably heard about water shortages we've had out west. They've had a lot of heavy rain in the last few months that has alleviated some of those water shortages and led to flooding. But agriculture is far and away the biggest water use. People are not drinking the vast majority of the water. Most of it is used to grow food, such as alfalfa that's used to feed the cattle, or almonds. Almonds use a ridiculously high amount of water. It's roughly 1 gallon of water to produce one almond. It's insane how much water almonds consume. A huge portion of California's water budget is spent on almonds, way more than people would drink or use for their lawns. It's massive. So agriculture is one of the biggest uses of water out west and in the rest of the country. And as more people move out west, the amount of water is the same or shrinking, and the demand is going up. So they're having to make tough decisions on water use out west. So they've gotten a slight reprieve with these heavy rains that we've had, but it won't last forever. So condensation in clouds, basically, condensation is when moisture in the air forms into little droplets of water that can eventually come down as rain or water vapor. And they need to have some particle that the moisture can kind of collect around, maybe a particle of dust or so on. And then condensation at the ground level is dew or frost. And in the sky, condensation would be clouds or mist or something like that. So fog often forms along the ground early in the morning where the temperature starts to rise, and then that has some of the moisture that's on the ground starts to dissipate and evaporate into the air, and that can cause fog. This here is condensation near the ground in the form of fog. This is East Africa, but parts of Jackson look the same. When I drive my kids to school towards Western High School, we drive by a big field that looks a lot like this in the morning many days, where there's lots of mist. So here is a diagram of some of the main types of clouds here. Nimbus stratus, stratus clouds, cumulus clouds, and so on. You can kind of read about this on your own. But there are lots of variations in different kinds of clouds. The clouds high up in the atmosphere that are kind of wispy and feather-like are cirrus clouds. And the ones that are most likely to have rain are the cumulus clouds, and they can appear at different heights in the atmosphere. So when you have precipitation, it usually comes down as rain or snow, which we're familiar with. Also, it can come down as sleet, and that's ice that forms, then melts, and then refreezes as it's coming down to the ground. Freezing rain is rain that hits the ground and then freezes once it hits the ground. That can be very dangerous to drive on. And hail are little ice particles that grow within the clouds in strong updrafts and then come down as large chunks of ice. And then grauwolp are soft particles of melted hail, which are fairly rare, but occasionally you'll see weird, sort of like fluffy snowflakes that look almost like salt you'd put down on your walkway to melt the ice. And that's actually kind of light, fluffy, melted hail called grauwolp. And here's some more forms of precipitation. Rainstorm coming down to the Ponderosa Pine Forest in Flagstaff, Arizona. A falling snow accumulating in south central parts of Alaska. A freezing rain in North Yosemite National Park in California. And on the bottom right, balls of hail coming down in northern Texas. You'll often see hail during tornadoes and heavy rainstorms. So this is a record size hail. This landed in Nebraska. It's about 7.5 inches long, and it's one of the biggest chunks of hail that the National Weather Service has ever come across. It landed in Hastings, Nebraska. So hail can be dangerous if it gets real big. So different areas of the world have different amounts of rain, and often an area can be very dry year-round, it can be wet year-round, or it can have dry or wet periods. So when an area is consistently dry, they have what's called a water balance deficit. You can imagine a water balance is like a checking account. You have water come in, you have water come out. It comes in the form of rain or snow, and it leaves in the form of runoff or evaporation. Baghdad is consistently dry all year round. So there's a water deficit almost all year round, making it very dry. Tokyo, Japan, there's a water surplus, meaning more water is landing in Tokyo than the natural environment can absorb. And that surplus runs out into the ocean in the form of runoff. And then Faro, Portugal on the right has a surplus during the winter and then a deficit during the summer because they have a Mediterranean climate, which is cool and drizzly in the winter and then dry during the summer. So they have a little bit of both, with excess rain coming down during January, February, and then during July and August, a prolonged dry period where it dries out and there's far less moisture coming down than the amount that evaporates. And the water balance can vary significantly by latitude. Along the equator, there's far more rain coming down than would naturally evaporate. And then as you get further towards the poles, that shifts. And then as you get north of about 40 degrees latitude in the northern hemisphere, there's more rain coming down than would naturally evaporate. And then that's a pattern that stays pretty consistent until you get to the north and south poles. So more rain along the equator, more evaporation just north of the equator. Those are where most of the deserts are, about 15 degrees to 30 degrees north and south latitude. And then as you get a little bit beyond 30 to 40 degrees, you'll often have a rain surplus again. So the amount of rain varies depending on the latitude. This here is a global distribution of annual evaporation and evaporation transport. Basically, it kind of shows the amount of rain on average. And as you can see, the equator has heavier rain. And as you get deep into the interior of continents, it's a lot drier. The Sahara Desert in northern Africa, there's very little rain. And then in the central part of the Indian Ocean near the equator, there's very heavy rain all year round. So you've heard probably about the atmospheric river that's been hitting Los Angeles. Atmospheric rivers are narrow, winding corridors of rain, usually about 250 miles wide and 1,200 miles long. They can carry vast amounts of water vapor. They are a lot like a river of moisture in the air. The flow rate is comparable to the Amazon River or other large rivers, meaning the amount of water that these carry are similar to a very large river, and they can last up to 2 or 3 weeks long. So a few of these atmospheric rivers have been pounding south central California, Los Angeles to San Francisco, causing flooding, but also helping alleviate the drought that they've had too. All right, precipitation and air masses and fronts. We'll try to get through these last sections fairly quickly. I don't want to keep you here too much past an hour. This is a picture of different air masses coming together. This is common where you have a cold front moving into a warm front. You'll see this disturbance where clear skies will meet up with clouds. An air mass is a large body of air with a relatively homogeneous characteristics. So a large air mass will have roughly similar temperature and similar moisture content compared to a different air mass. Classifications for air mass are MT, MP, CA, CP, and CT. And M stands for marine, C stands for continental, and T stands for tropical, P is polar, and A is Arctic. So there are no maritime Arctic air masses, but there are these other kinds of air masses. So here's a picture of air masses in North America and where they often come from. So Mediterranean tropical air masses will often form in the Atlantic or the Gulf and move into the northern part of North America. And maritime uh, polar or continental polar air will often come from the Arctic and Canada over the central part of the US. So when you have warm, moist air from the Gulf mixing with cold, drier polar air from Canada, that's where you often have tornadoes and major thunderstorms. And that's why the US is so prone to tornadoes. We have about 80% of the world's tornadoes. So about 4 out of 5 tornadoes that hit anywhere in the world hit in the US. And a lot of that is in Tornado Alley. So different weather patterns form in different areas and then move into North America and other parts of the world. So lifting mechanisms that produce precipitation, these are different ways that rain and snow can happen. Convergence is when similar air masses converge or move together and they're forced to rise, forming clouds. Convection is when surface heating causes air particles to rise and form clouds. That's often what you get when moist air from the ocean moves over dry, hotter air over land. A frontal is when warm and cold air masses meet. Cold air lifts the warmer air, forming clouds. And orthographic is when you have moist air being pushed up into mountains, and that cools the air, and then that comes down as rain or snow. And then the opposite side of the mountain range is usually a lot drier. That's called the wind shadow. So here we have a snapshot of lifting and convergence. These are basically just kind of global weather patterns of moisture around the world. In January, you can see along the equator, there's consistent rain. And then in South America, their summer, the Amazon basin gets a lot of rain during January, which is their summer. And then during July, summer of the Northern Hemisphere, you have lots of rain. In India, you can see that's monsoon rain. You can see lots of rain in Japan and parts of the Pacific just north of the equator. So you tend to have more rain near the equator, just below the equator during a hemisphere summer. That's when you typically have the most rain. So this is convection precipitation. This is just kind of a diagram of warm air and cold air and the movement between warm and cold air within clouds. This is an example of a cumulus cloud. A, warm air is being moved up into the cloud, forming snow. B, as you can see, that warm air in the top of the cloud tends to cool and come down as rain or snow. And then, as you can see in the third one, the energy and the moisture tends to dissipate and the clouds tend to break up once the moisture has been used up. So this is a diagram of convection precipitation. So you've probably heard of warm fronts and cold fronts. A warm front is when you have warm air that moves over colder air and it's pushed up. It's usually a larger, it's not as dramatic, the change is not as perceptible. Usually warm fronts mean warmer air and possibly some drizzle. Cold fronts are much more dramatic. That's when you have cold air moving usually fairly quickly that bulldozes warm air out of its way, pushes warm air up. That often can lead to heavy rain as the moisture gets pushed up into the atmosphere and it cools and comes down as rain. And these are usually a lot more dramatic, and this is where you have a lot of the big storms at these cold fronts. This is kind of a cross section of a typical storm cloud you might see during a heavy rainstorm. You'll often have a cloud that's moving, let's say, from west to east in this diagram, and there's an annular part of the cloud that reaches up ahead of the rest of the cloud. And then on the bottom of the cloud, about halfway through the cloud, you have what's called a squall line, and that line is where you start having the heavy rain and snow. It's usually about halfway through the cloud. And then as you get towards the end of the cloud passes, the cold air and moisture and rain tends to come down, and then it kind of dissipates, and then the cloud passes. But the heavy rain is in the back half of the cloud, and then the front half of the cloud is usually a little drier and windier. So tornadoes and their impacts, as I mentioned, tornadoes, about 80% of the world's tornadoes hit in the US. We have about 1,000 per year, and they can cause significant devastation. We had a tornado that hit in Gaylord, Michigan last year, which is a little unusual for it to hit that north. I think it killed one person, injured a few others, and caused significant property damage. But as you can see here, Tornado Alley, where you have the highest concentrations of tornadoes, tends to be in the south central part from Texas, roughly up to southern Minnesota. This particular picture shows where tornadoes hit in 2011, a record year for tornadoes. And that year, there were a lot of tornadoes in the southeast compared to most years. Usually, you'd have more than in the center part. But this is one of the worst years we've had for tornadoes. 875 tornadoes altogether during that season, which is a near record. And usually they're in the south central part of the US, in the plain states and the prairie states. So the states that get the most on some, surprisingly, Texas, largely because of its size, gets about 150 per year. And then Oklahoma, Kansas, Nebraska, and so on can get many tornadoes as well. Wisconsin and Minnesota, I lived in Wisconsin for 6 years. They definitely got a lot more tornadoes than Michigan did. But the most of them are in the central southern part of the United States where they're hit the hardest. Here's some more information on U.S. averages of tornadoes. May is the busiest month. June is very busy as well, but they tend to hit in late spring most commonly. And then orographic precipitation. This is precipitation that's caused by moist air being pushed up into mountains, cooling down, coming down on the windward side of the mountain as rain and snow, and then the leeward side, or the side that's on the opposite side of where the storm is coming from, is usually drier and sunnier as well. So this is kind of a cross section of a typical pattern you'll see where moisture prevailing wind flow comes off the Pacific Ocean, passes over Eugene, Oregon. As it moves up, there's a dry lapse rate of moisture where the air basically starts getting pushed up against the mountain at about 3,000 meters, 10,000 feet. That's kind of the peak of the Sierra Nevadas and other mountains in this area. And then on the opposite side, it's a lot drier. You can see Bend, Oregon is kind of in the dry part of the mountain where they get a lot less moisture than Eugene, Oregon. So we think of Washington State and Seattle as being wet. Portland is wet and cloudy, but the eastern 2/3 of Washington State and Oregon are actually fairly dry. You can see here, this is Eugene, Oregon versus Bend, Oregon. This little blue line is basically that previous drawing that we saw, and it moves over the Cascades Mountains, and then on the leeward side, it's much, much drier. Bend, Oregon is actually kind of a booming town. It was 20,000 people in 1990, and as of 2023, it's 105,000, about the size of Ann Arbor. So it's increased by fivefold from 1990 to 2023. And part of the reason is it has a fairly nice mild climate. It technically is a semi-arid climate, which means it gets too much moisture to be considered a desert, but not enough to be considered like Michigan, which is a continental climate. So it's sunny, but it's not as dry as a desert would be. And there's some outdoor activity. So it's really kind of been a big boom town in the last 30 years or so. People moving from expensive cities like San Francisco, Portland, and Seattle to Bend, Oregon, and it's increased fivefold. So weather systems, we'll focus mostly on hurricanes. There are other weather systems like easterlies and so on, but hurricanes are kind of the most interesting and consequential of the weather systems in this particular unit. This here is a cyclone, as you can see on the left part of this picture. And on the bottom right, Great Britain is in what's called an anticyclone, which are basically opposite weather patterns of a cyclone. And this is a cyclone or hurricane that's kind of moving slowly towards the British Isles. A cyclone, again, is a general term for any large low pressure center. A cyclone that hits the southeast is usually called a hurricane. The similar storm that would hit the Pacific would be called a typhoon, even though it's more or less the same thing. And then sometimes in the southern hemisphere, they're called cyclones, but that just sort of is a generic term for any large low pressure storm. So this is a snapshot taken from space of several different hurricanes that were hitting at the same time. You can see there's a hurricane named Hurricane Bill, Hurricane Claudia, and Hurricane Anna that are forming over the Gulf, moving towards the southeast part of the U.S. And you can see there's a thin line of clouds at the intertropical convergence zone that's along the equator. They have very few hurricanes along the equator, but they often have some consistent cloudy, rainy weather. And this is just kind of a snapshot of major weather systems moving towards the U.S. I believe this was taken in August 17th of 2009. So that's what they look like once you can see them from space. Because the satellites were much more aware of approaching storms than they would have been even 50 years ago. So those have been very helpful. So hurricanes can form over warm water. It usually has to be 80 degrees Fahrenheit or 28 degrees Celsius. If there's a disturbance in the ITCZ, and if there's sufficient Coriolis effect, most hurricanes form 8 degrees to 15 degrees north and south of the equator. And they are weaker air can can destroy the formations. In other words, if you have something that's forming, but then it loses energy, it can kind of dissipate before it becomes a hurricane. So hurricanes can all form over tropical oceans where these conditions are met. So the Atlantic is a very common place for hurricanes to form, especially just north of the equator. So this is an example of Hurricane Mitch, a major hurricane that hit the United States and Honduras. Honduras was really hit hard by this. There were about 10,000 deaths because of this hurricane. 1/4 of the country, 6.4 million people, were homeless because of this hurricane, and it caused significant damage that took years for Central America to recover from. So that's one of the worst hurricanes to hit Central America recently. So this is kind of a cross section of a hurricane. If you were to take it and cut 1/4 of it out and look at it, the center part is called the eye of the storm. That's clear. You have wind coming from vertical down towards the surface in the eye of the storm. Just outside the eye, you have the eye wall where you have some of the strongest winds. Greatest wind speeds are about 18 kilometers from the eye in this area called the eye wall, where you have the heaviest precipitation and wind. And then from the eye wall, there are kind of bands of the hurricane where you'll have relatively clear weather followed by heavier storms and so on, kind of moving out as they spin in a counterclockwise formation in the northern hemisphere. So the eye is the peaceful part in the center. The eye wall is the heaviest, strongest winds and the heaviest rain just outside of the eye of the storm. So you've probably heard of different classifications for storms, Hurricane 1, Hurricane 5, and so on. There are categories that are 1 to 5. These are broken down by what they're categorized by. This chart shows the wind speed of a hurricane, what is likely to happen, what the description of the effects are. Recently, Katrina that hit New Orleans was a fairly strong hurricane, but it was only category 3. It caused a lot of damage because the levees that protected New Orleans broke, and that flooded the city, and that's what caused a lot of the hardship and problems. So it was an infrastructure failure. That was considered a category 3 hurricane. The worst is category 5. This is basically a snapshot of where hurricanes are likely to strike. As you can see, along the equator, there are very few. And in the Atlantic, about 8 degrees latitude to 15 is where most form. A lot of them wind up moving towards the west and then hitting the southeast parts of the United States. Florida is very vulnerable. And then probably the most is in the western part of the Pacific, along the Philippines and Indonesia. There they get hammered with lots of hurricanes, and you can see they have more there than any other parts of the world. They're called typhoons in that region, but they're the same thing. So as you can see, they're not evenly distributed. Certain areas are more prone to hurricanes than others. This is the North Atlantic hurricane season. They often peak in late summer, early fall. Hurricanes and tropical storms. This is kind of a breakdown of those. The most recent hurricane to hit the United States was Hurricane Ian, which was a Category 4 hurricane, and that hit in 1992. And it was the third costliest weather disaster on record for the United States. It hit Florida especially hard, especially the west side of Florida. It was the deadliest hurricane to hit Florida since 1935. There was an even worse hurricane called the Labor Day hurricane then. And 160 people were killed and about $113.1 billion of damage were caused by Hurricane Ian. So that's the most recent hurricane to hit the U.S. So that's basically weather patterns. Again, there are other weather patterns in this chapter, in this unit, but we've all gone past an hour, so we're just going to focus on hurricanes. And if you have any questions, you can send me an email, or if you have a microphone or you have a chat feature, you can send that to me now. Does anyone have any questions about this that we've gone over? Otherwise, thank you for joining me. I will post this online. I know some people weren't able to view it because I didn't put it in the proper location, but I will post a version of this online and make sure that it's accessible if you were not able to join us. So thank you for joining us and have a good evening.
You are currently the only person in this conference.